we found out how we can find the uncertainty of a physical quantity. We can find the absolute, we can find the fractional or percentage uncertainty as well. Now, you hardly get a question in which they ask you to find uncertainty of a single physical quantity. Matter of fact, in most of the questions, especially in paper 2, 3, 4 marks questions, you're asked to find the uncertainty of an expression which comprises of plenty of quantities. Okay, for example, they ask you to find the uncertainty in density. Then you realize the formula of density is mass over volume, so you need to find the uncertainty in mass, you need to find the uncertainty in volume. Then these are being divided, mass and volume are being divided, so there's a special case. The situation is if the quantities are being multiplied or being divided, then you have to sort out the individual uncertainties in a different way. If they're being added, then that's a different case. If there's an exponent, there's a different case. So we'll go through all of those cases one by one. Now the first one is if the quantities are being added or subtracted. So what do we do in that case? The uncertainties will be added. The uncertainties of both the quantities which are being added or subtracted, whether they are being added or whether they're being subtracted. But for the uncertainties would be added. So for example, there's a quantity A1 and there's another quantity A2. Okay, so it can be anything. They can be masses, they can be densities, they can be speed, force, or anything. So the total uncertainty, alright, so first you need to, the formula says that you're adding the two quantities. Okay, now you need, this is the quantity that you're measuring through the experiment. Now the uncertainty in x would be represented by delta x, and the uncertainty would be equal to uncertainty in the quantity A plus uncertainty in the quantity 2. So if you have n number of quantities, like you're adding a big number of quantities, all you have to do is, in order to find the uncertainty in your final answer, you have to add the individual uncertainties one by one. Right? You have to add the individual absolute uncertainties for n number of quantities. Here you have the first example. The diameter of the inner tire is, the outer tire is 55 and the uncertainty in that is 0.5. Okay, it's already given. It's the absolute uncertainty. The diameter of the inner tire is 21.0 and the uncertainty is 0.7. That's also given. The question says find the difference in the diameter. Okay, that demands you to only subtract the diameters to find the difference in the diameter, but you have to find the difference in diameter within the uncertainty. So you need to consider the uncertainty of the inner tire and of the outer tire as well. But first of all, let us find the difference in the diameter. So the difference in the diameter, I can write it as d1 minus d2 because d1 is the greater one, and if I subtract these two, it will be 55 minus 21. And, and what do you get from here? You get 34.0 centimeters. Okay, so this is the final value for the difference in diameter. But how much uncertainty is there? What you have to do is add the uncertainty of the first one and the second one. So from the first one, the uncertainty was 0.5. The second one, the uncertainty was 0.7. So the total uncertainty, that equals the uncertainty of the first one plus the uncertainty of the second one. Then you hit it on the calculator, you get 1.2 centimeter. How do you write your final answer? First you write the physical quantity. We call it principal value. So you write the principal value first, which is 34.0, followed by plus minus 1.2. followed by the unit. So this is how you find the total uncertainty when the quantities are being added or subtracted. So you see in this one, the quantities were being subtracted, but the uncertainty would always be added. Keep it in your mind. Let's move on to the next case. If you have a coefficient, okay, when a coefficient is being multiplied by a linear variable. So what do we do in that situation? So for example, you have an expression that says x equals to a, but not a, there's a coefficient of it, n times of a. So what are the examples? Find the perimeter within the uncertainty limit. So you are given with the rectangle, the principal value of the rectangle along with the uncertainty. This is, you can call this one the length, and the width is also given. The principal value followed by the uncertainty. And you need to find the perimeter of the rectangle within the uncertainty limit. So first of all, let us find the perimeter. Let us find the principal value of the perimeter first. So for that one, we can simply use the formula. We have perimeter equals 2 times length plus 2 times width, or you can take 2 common. And that equals to 2 times the length was 10. I just copied the values from there. And the width was 6. Then you hit it on the calculator as it is. For this one, you don't even need to meters. All right, let me check it in meters. Yes, it is in meters. So we write meters with the answer. So this is the principal value of the perimeter. We need to find the uncertainty as well. So in order to find the uncertainty in the perimeter, I'm going to write it as delta P. P is the perimeter and delta P is the uncertainty in the perimeter. And that would be equal to 2 times the uncertainty in length plus 2 times the uncertainty in width. Because you have 2 as a coefficient here. So whatever the uncertainty of length is, you multiply by 2. And the uncertainty of length is given 0.3, uncertainty of width is 0.2. Let's insert the values here. Then you hit it on the calculator, you get 0.6 from here, 0.4 from here, 1.0. Alright, now we write the final answer as principal value plus minus the uncertainty. So it will be 36.0 plus minus 1.0 followed by the unit meters. So this is how you find the uncertainty when there is a coefficient of a linear variable. Let us now move on to the case number 3, and this is the case number 3 is the most important one. You generally get a question in paper 2. If you take a look at the most recent past papers, you always get a question from this one, and this is generally 3 to 4 mark questions. The quantities are being multiplied, and at the same time some of the quantities are being divided. So for multiplication and division, it's just the same thing. For example, if you want to write as centripetal force, or let's say easy example, density equals to mass over volume, what you can basically write as density equals to mass multiplied by 1 over volume. So density equals to mass times the reciprocal of volume. That would be the same thing. Alright, so in this situation, when the quantities are being multiplied or divided, in order to find the uncertainty, the total uncertainty, what you have to do is add the percentage uncertainties of the physical quantities. Add percentage uncertainties. How do we find the percentage uncertainty? We discussed it previously. There is absolute, there is fractional, and then there's percentage uncertainty. All three of them we calculated in the previous part with the help of examples. If you're not clear with it, you gotta refer to the previous part. So let's say you're finding a physical quantity, and in the formula of it you have to multiply a number of physical quantity. Let's say A1 times A2 times A3 times A4, A5 up till AN. And stand for AN stand for it can be any number. If it is 10, then it'd be like A1 times A2 times A3 till A10. Alright, and represents any number of physical quantities, and all of them are being multiplied. So in order to find the uncertainty in X, which will be written as delta X, we'll be writing as percentage. If the quantities are being multiplied, we'll be finding the percentage uncertainties of the physical quantities, and then we'll add all of them. So the percentage uncertainty of A1 would be delta A1 percent. Percentage uncertainty of A2 would be delta A2 percent. Percentage uncertainty of A3 would be delta A3 percent, all the way to the number of quantities that you have. So you add all of them. Alright. Now, how do we apply this rule? The rule is very easy. You just need to follow the steps. The general thing is to combine the multiplication and division with the exponent rule as well. So generally the rule number 3 and rule number 4 are combined, but matter of fact these are exactly the same. I'll explain how rule number 3 and rule number 4 are same. Anyway, first we move on to an example. Find the speed of the vehicle along with the uncertainty. So speed equals to, we recall the formula for speed. Speed equals to distance over time. The distance is 50.0 divided by time is 5. So you get speed as speed equals to 10.0 meter per second. This is the speed. Alright. This is a principal value of speed, but we need to find the uncertainty as well. Like how much uncertainty is there? If this is V, let's call this is V. Speed is represented by V. So this is a value of V, but what about the value of delta V or delta V percent? In the formula of speed we have distance and we have time, and these two quantities are being divided. So we'll apply the rule here. The rule says if the quantities are being divided or multiplied, then you have to add the percentage uncertainties of the individual quantities. So first we find the percentage uncertainty of distance, then we find the percentage uncertainty of time, then we add both of them. Alright, percentage uncertainty of distance plus the percentage uncertainty of time, and that would give you the total percentage uncertainty in the principal value. Now in order to find the percentage uncertainty in distance, we discussed the formula. It'll be absolute uncertainty divided by the value times 100. Alright, we discussed it already in the previous part, how to find the percentage uncertainty. So in this situation this will be 0.2%. Now let us find the percentage uncertainty in time. So that'll be 0.05 divided by the principal value, which is 5.00, multiplied by 100. And if you hit it on the calculator, you get 1%, 1.0. Okay. So we found out the percentage uncertainty of distance, we found out the percentage uncertainty of time, then we find the total percentage uncertainty by adding both of them. So the percentage uncertainty of speed would be equal to the sum of percentage uncertainty of distance and the percentage uncertainty of time. So that'll be 0.2% plus 1.0%. So what do we get from here? We get delta V percent equals to 1.2%. Alright, now there are two different ways you can write the answer. Either you can write the answer as it is, which is the final value of speed equals to 10.0 plus minus 1.2% meter per second. Alright, this is one of the way you can write the final answer. The final answer is written with the percentage uncertainty. Or the next thing is, or the other way is, you can find out how much of this 1.2% of 10 exactly is. You can calculate it. You can find 1.2% of 10. So there'll be 1.2 divided by 10 multiplied by 100, and that is 0.12. Okay, so we're writing the absolute uncertainty with the principal value. This is the other way you can write the uncertainty. So it is 0.12. I'm going to raise it off. 0.12 we got from here. So we can write as V equals 10.0 plus minus 0.12, not with a percentage sign now, because we found out how much 1.2% of 10 is, and that is 0.12 meter per second. The last thing is, you need to write the uncertainty with certain rules. There are certain rules by which you have to write the uncertainty with the principal value, and like I said, I'll explain the rules in a separate video, but for now I'm going to tell you, you should be having equal number of decimal places in the uncertainty as of the principal value, or it can be less than that, but at least equal to the principal value. You cannot have more number of decimal places in the uncertainty compared to the number of decimal places in principal value. So in this value you have only one decimal place. The uncertainty should also be having at least one decimal place, at most one decimal place. So V equals to 10.0 plus minus 0.1. If I round it off to 1 dp, one decimal place, it will be 0.1 meter per second. So you can leave the answer as the first block or as the second block, or sometimes you have no choice, you have to answer as the way it's being demanded in the question. Alright everyone, so let's move on to the case number 4. Once again, like I said, they combine, the examiner, he combines case number 3 and case number 4. Alright, it's a very common practice that they combine case 3 and 4, and matter of fact, case 3 and case 4 are basically the same thing. Alright, for example, I'm writing as y equals to x cubed. Then the same thing can also be written as y equals to x times x times x. So you can apply the case rule number 3 also here, which is you add the percentage uncertainties of all the physical quantities. Okay, or what you can do is you can find the percentage uncertainty of x and multiply it by the exponent, and that's it. That's pretty much it, and I'll explain with the example also, but first let us complete the steps here. So what you do here is you multiply. Okay, so that's it. That's pretty much it. So you can write it as a percentage uncertainty. So if you have an equation that looks something like this, y equals to a raised to the power n, the exponent is n. N means the exponent can be anything. It can be 2, 3, 4, 5, 6. If it is 1, then the exponent, it would be treated as the case number 2. So the percentage uncertainty in y equals the percentage uncertainty of a multiplied by the exponent. So n multiplied by the percentage uncertainty of a. And if you want to write as fractional uncertainty, that is just the same thing. It'll be written as delta y over y and that equals to n times the fractional uncertainty of A, which is delta A over A. Alright, the conversion of fractional and percentage uncertainty we explained already previously. So here we have a sample question. The radius of a sphere is 2.50 plus minus 0.02 centimeter. Find the volume along with the uncertainty. So first I'm going to just find the volume and then we do the uncertainty as well. Radius is 2.5. Keep it in your mind. The formula for volume of a sphere is 4/3 pi r cube. We got to speed up here. Alright, just a question of mathematics. 4/3 as it is. The value of pi, you can just write pi as it is on the calculator, or 3.14 times the cube of 2.50, and then you hit all of it on the calculator, you get 65.5 cubic meters. Alright, this is the principal value. We didn't calculate the uncertainty yet. Now in order to calculate the uncertainty, you have the physical quantity that you have is the radius only. Everything else is just a constant. Forget about the constant. The physical quantity is radius. And this raised to the power 3. The exponent of the radius is 3. So you find the percentage uncertainty of radius. You multiply it by 3, which is the exponent. And that gives you the value of the total percentage uncertainty in volume. Alright, so I'm finding the uncertainty here. So uncertainty in volume, percentage uncertainty in volume would be 3 times the percentage, uncertainty in the radius. Okay, 3 times the percentage uncertainty in the radius. Now what is the percentage uncertainty in radius? It would be 0.02 divided by 2.50 multiplied by 100. Okay, we studied that already. 0.02 divided by 2.5. Once again, if you don't know how to find the percentage uncertainty, please take a look at the previous part of the video. So this will be 3 times, what do we get here? We hit it on the calculator, we get 0.8, and that equals to 2.4%. And once again, there are 2 ways you can write the final answer. Either you can leave the final answer with the percentage uncertainty, or you can write the final answer with the absolute uncertainty. So it will be 65.5 plus minus 2.4%, and the unit would be cubic centimeters. Or if you don't want to write in percentage, you want to write the absolute uncertainty here, or they ask you to do so, you have to check out how much 2.4% of 65.5 is. Alright, so it will be 65.5 plus minus, and then you can find 2.4 divided by 65.5. Sorry, 2.4 divided by 100 times 65.5. So you can find out how much 2.4% of 65.5 is. That will be written as plus minus, with plus minus sign with the principal value. But there, in this situation, there will be no percentage sign of it. There will be no percentage sign here because we have gotten rid of the percentage uncertainty. Alright, so either way you can write the final answer. So generally, like I said, generally they combine the case number 3 and the case number 4, because they can ask you, they can give you a formula where you have to apply the rule number 4 as well as the rule number 3. So here we have another case, uncertainty in the average value of measurement. So for example, you were taking readings from the micrometer. The first reading that you took was 1.20, then the second one 1.22, 1.23, 1.19, 1.22, 1.21. These are 6 readings that you have taken by the micrometer. It might be diameter of a wire or anything. You have taken 6 readings. Now you need to find the mean reading, the mean diameter, along with the uncertainty. So first of all, let us find the mean diameter. All the values, 1.12 plus 1.22 plus 1.13, the sum of all the values divided by the number of values. Then you hit it on the calculator, you'll get the average diameter as 1.21 millimeter. Okay, just hit it on the calculator. Find the sum of all of it divided by the number of values. This is the average diameter that we have. Now, how much uncertainty is there? In order to find the uncertainty in this situation, you have to find the mean deviation of each reading from the average value. So find mean deviation. Let me write it over here. Mean deviation of each reading from average value. So what is the average value? The average value is 1.21. Keep it in your mind. The average value is 1.21. Sorry. Now, what is the deviation of this quantity, the first value, from 1.21? What is the difference? There is a difference of 0.01. There is a difference of 0.01. Now, what is the difference between the second quantity and the average value? That is again 0.01. How about the second one? You subtract these two, you get 0.02. How about the third one? Once again 0.02. Fifth one 0.01. The last one 0. So these are the deviations of each quantity from the average value. What you do now is you take the mean deviation. So these are your deviations. You want to take mean value of these deviations. So you add all of them and divide it by the number of deviations, which is 6. So what you do here is the percentage, the uncertainty in the average value would be the mean deviation, 0.01 plus 0.01 plus 0.02 plus 0.02 plus 0.01 plus 0 divided by the number of values that you have, which is 6. So what is the mean deviation? You hit it on the calculator and the mean deviation would be 0.01, and then you write the final answer. Average equals to principal value, which is 1.21, plus minus the mean deviation millimeters. So this is how you write your final answer. This is how you calculate the uncertainty for the situation in which you're finding the mean value of a number of values. So that was your case number 5. Moving on to the next one, that is case number 6. We have a bit of misprinting here. That is case number 6. And the case number 6 is the last one. It is the uncertainty in the timing experiment. Alright, so you're doing an experiment that involves the measurement of time with the help of a stopwatch or anything. It involves the measurement of time, generally with the help of a stopwatch, because we'll be measuring a small interval of time. For example, you might be measuring the time period of a simple pendulum or anything like this. So what you have to do is, I'll explain this one for with the help of an example. The time of 30 vibrations of a simple pendulum recorded by a stopwatch, accurate up to tenths of a second. What is this? Accurate up to tenth of a second. This is giving you this has given you the least count. This has given you the precision of the stopwatch. Accurate to tenth part of a second is 0.1 second. The minimum that it can measure is 0.1 second. Accurate to hundredths part of a second, up to hundredths of a second would have been 0.01. Accurate to thousandths of a second would have been 0.001. Alright, so they have given you the least count, they have given you the precision indirectly. And the total number of vibrations you have taken is 30. And what is the time for 30 vibrations? 54.6. Find the period along with the uncertainty. So for period, in order to find the period, I'm finding the principal value first. Principal value here. And here we'll be finding the uncertainty. So let us find the principal value. In order to find the time period, you know what we have to do is to divide the total time by the number of oscillations. Capital T stand for the time period, small t stand for the total time. The total time was 54.6 and the number of oscillations were 30. So what do we get here? The time period of one oscillation would have been 1.82 seconds. Okay, 1.82 seconds. Then we need to find the uncertainty in the value of time period. So uncertainty in t would be represented as delta t. In this situation we find the absolute uncertainty, unless it is they ask you otherwise. So delta t would be equal to, what is the rule? The rule says divide least count by number of oscillations. So what was the least count? Up to 10th part of a second. So the least count was 0.1 divided by the number of oscillations. We repeated the experiment 30 times. We took 30 oscillations. We let it move around by 30 complete cycles. You hit it on the calculator, you get 0.003 seconds. So the final value would be written as 82 plus minus principal value plus minus the absolute uncertainty in this case. Now according to the rule, like I told you, one of the rule, the number of decimal places in the uncertainty should be equal to the number of decimal, at least should be equal, not sorry, at least, at most it should be equal to the number of decimal places in the principal value. How many number of decimal places do you have in the principal value? You have only 2 decimal places, but the uncertainty is 3 decimal places. But the thing is, we cannot reduce it to 2 decimal places, otherwise it would be rounded off to 0.00. If you reduce it to 1, it would be 0.0. If you reduce it to a whole number, it would have been 0. So we cannot reduce this one to lower number of decimal places because it has only one significant figure. What we can do is we can add another decimal place here. So 3 dp here and 3 dp here. So this is how you can write your final answer of the experiment in which you're finding the average time by taking number of oscillations. You can find the uncertainty by dividing the least count of the instrument by the number of oscillations. So you see, in this situation you realize something. The more the number of oscillations you have, let's say instead of 30, we write here we have taken only 15 oscillations, or let's say 10 oscillations. So if we take less number of oscillations, then the uncertainty would have been increased, which is a bad sign. We need to lower the uncertainty as much as possible. That's why in the experiments which involved the use of stopwatch and you have to take number of oscillations, it is always recommended that you take plenty of oscillations, so the uncertainty of the experiment would be reduced. I'm going to write the same thing here. The uncertainty of a timing experiment, you have to take large number of oscillations. The more the number of oscillations, the lesser the uncertainty with the principal value. Alright, so let us solve another sample question. This is from a very recent past paper. The mass of the cube of aluminum is found to be 580 grams. I can convert into, okay, let's not convert into kilograms because the density has to be calculated in grams per cubic centimeter, so we'll leave it as it is. So mass is given, this is a mass given, and with an uncertainty in the measurement of 10 grams. So plus minus mass, the value of mass would be 580 plus minus 10 grams. Alright, with the uncertainty would be written like this, and the length of the cube is 6. With the uncertainty of plus minus 0.1 centimeter, we need to find the density of the aluminum. So let us find the principal value first. Here we find the principal value, and only afterwards we'll find the uncertainty. So for the principal value, we have density equals to mass over volume. So mass divided by volume would be L cube, because that's a cube. So mass was 580 divided by the cube of 6. So 580 divided by 216, you hit it on the calculator, you'll be getting 2.69 grams per cubic centimeters. This is the principal value, but we need to write the uncertainty as well. And what uncertainty do we need to write? Absolute or percentage? Absolute, because there's no percentage sign here. Okay, so the uncertainty would be, so you see in the formula for the density there is mass and volume which are being divided, and if they're being divided, then that means you need to add the percentage uncertainty of mass and that of the volume. So the total uncertainty in density, delta D percent, that equals to the percentage uncertainty of mass plus the percentage uncertainty of volume. Now what is the percentage uncertainty of mass? Let us find the first one, percentage uncertainty of mass. Percentage uncertainty of mass equals to 10 divided by 580 multiplied by 100. Once again, I explained the percentage uncertainty in the previous part, you can check it out there. What you get from here is 1.7%. Okay, just hit it on the calculator. Now what is the percentage uncertainty in volume? The percentage uncertainty in volume would be calculated by rule number 3, sorry, by rule number 4, because you have L cube, you have the cube of length, so that'll be 3 times the percentage uncertainty of L. Scroll up, go to the rule number 3 and check it out there. Sorry, the rule number 4. So 3 times the percentage uncertainty in L, which would be 0.6 divided by 6, 0.1 divided by 6 multiplied by 100, and what do you get from here? You get 5%. So 5% is the percentage uncertainty volume, 1.7% is the percentage uncertainty in mass. What is the total uncertainty in density? You add these two, so this will be delta M was 1.7% plus 5%, so the total uncertainty in density would be 6.7%. Alright, 6.7%. Keep it in your mind, 6.7% is the total density. So 2.69 plus 6.7% grams per cubic centimeter. But without the percentage sign, you can find how much 6.7% of 2.69 is. Or okay, or what is 6.7% of 2.69? So that'll be 2.7 divided by 100 multiplied by 2.69, and from here you get 0.18. okay, you get 0.18. So now let me write the principal value. The final answer for density would be written as the principal value. The principal value was 2.69 plus minus 0.18 grams per cubic centimeter. Okay, so you write the answer like this, you'll be getting 4 marks out of here, because the question says express your answer to an appropriate number of significant figures. So you have to consider the number of significant figures which would be compatible in this situation. This is what your last 1 mark is for. You leave it till here, you'll be getting 4 marks, but for the last mark you need to compensate the significant figures. First of all, how many significant figures should be there in the principal value? So in order to find the principal number of significant figures in the principal value, you see what are the lowest number of significant figures in the data, in the raw data. What is the raw data? This is your raw data, 580. And in 580, the number of significant figures are 2, because the instrument is able to measure only 10 grams, not less than that. If the instrument were able to measure to 1 gram, the number of significant figures would have been 3. And the other raw data, or the easier one, is 6.0. What is the physical quantity here? What is the value 6.0? How many significant figures? 2. 6 and 0. So the lowest number of significant figures in the raw data is 2. The number of significant figures in the principal value should have also been 2, not more than that. So this would be rounded off to 2.7. We cannot have 3 significant figures in the answer if the lowest number of significant figures in the raw data is 2. Okay, so I explained this one in significant figures. Now, according to the rule, the number of decimal places in the uncertainty cannot be more than the number of decimal places in the principal value. How many number of decimal places do you have in the principal value now? Once it is rounded off to appropriate number of significant figures, you have only one decimal place, which is 0.7. So the number of decimal places in the uncertainty would also be 1. So the final answer for this one would be 2.7. I'm writing there at the top, plus minus 0.2 grams per cubic centimeter. So you see, in this question of 5 marks, they have asked you pretty much everything of this chapter.